Hey everyone, welcome back. So we're going to be continuing on with logarithmic functions, and today is all about just the graphs, the transformations, the usual stuff we see every time we look at a new function. So our goals are just taking a look at how to graph them, what maybe we should look for in a graph, and then the transformations, so what are those key values, and then how do we identify them, what effects do they have, and then there's just some other sort of stuff that we should take a look at, such as average rate of change, domain, and range as well. So essential questions for today: what are the key points that we should look for? And then how can I identify the transformations? And if I have a question like where's the x-intercept, y-intercept, average rate of change, and so on, how do I do that maybe algebraically and from looking at a graph? So last class we looked at the relationship between logarithmic and exponential functions. We looked at the laws of logarithms, which I hope at this point you have written down, you've started committing to memory. We're converting between logs and exponentials to try and maybe solve some exponential equations. And then we're going to eventually focus on just trying to solve logarithmic equations, which may or may not involve switching between the forms, but will probably stay more so in the logarithmic functions from now on. Okay, so when we look at the graph of a logarithmic function, we can see two different ones up here. Where's my labels? Here they are. So we got y equals 10 to the power of x. There's our exponential function, the blue line. The logarithmic function is the inverse of it. So remember, inverse function is going to look like a reflection over the line y equals x. That's why we have the dash line in there. And it has this vertical asymptote, and then it curves off, and then it just climbs towards positive infinity forever at just a slower rate each time. So it's like, rather than an exponential function which grows at a faster rate every single step on x, the logarithmic function grows slower but still continues to grow. So it is still approaching a positive infinity value. But there is a horizontal asymptote, which is also key. Okay, so a couple of things. The vertical asymptote is going to be equal to our h value. So that's kind of one that we want to keep an eye out for. So the h value is inside of the log function. The b value is not like b like our other ones. Same thing with exponential functions. The b value is our base value, not a horizontal stretch or compression. We're only going to concern ourselves with a, so the vertical stretch compression in this unit. If you go into any more like higher or difficult levels of math, maybe you might bring back in the horizontal stretch compression, but not in this one. And then k is going to be that vertical translation up down, same as usual. So the vertical asymptote is the same as the h value. So remember, in an exponential function, you have a horizontal asymptote, which was our k value. This time we have a vertical asymptote, which is our h value. There's two reference points. So the reference points are those whole number coordinates. We've got one at the horizontal asymptote plus 1. And it's also our k value will give you that first reference point. And then we've got the, whatever the base value is. So in our case, this was 10. So 10 plus 1 is 11. So we can't really see this one. It's out here somewhere, but that's the next reference point. And it would be one step up from the k value. So if it's k value 0, it's going to be at, in this case, it would be 11.1. So at 11.1, there would be another reference point if we kept this graph going. All right, so I already talked about these, but identifying the asymptotes and the two reference points is an important thing for us to do, especially if you're asked to do it in a question, like give me two coordinates that belong to this graph, because with logarithmic functions and exponentials, there aren't a ton of whole number coordinates. So knowing those two reference points is sometimes key for being able to graph some of these functions. So if we look at this one, the h value is 1, which means the asymptote is at x equals 1, not y equals 1, x equals 1. And then our reference points, so looking at the key up top for how to do reference point 1 and 2, reference point 1, we take the h value plus 1, so h plus 1, and then the k value, and there's our first reference point, and then the b value in this case is 2, so that's the base value, plus h, and then the a value plus k, so a in this one is minus 2. So a, h, and k. And I guess B is important to mark here as well. So those would be our 2 reference points, and then we've got our asymptote. So if you were asked to graph a logarithmic function, I would expect to see an xy axis. I would expect to see the vertical asymptote marked incorrectly. So, get your vertical line tool out, and then your 2 reference points. So we've got 2, -2, and then 3, -4. And then we can see that because there's a -2 in here, this has caused a vertical reflection. So it would look something like this instead. So I would expect to see the asymptote and the 2 reference points graphed accurately, the axes in there, and then the rest of it is a freehand sketch. All right, so transformations, we've already kind of talked about this a little bit. There's not much else to go on. So we've got an a value of -5. That gives me the reflection. So the a value is the reflection of the x-axis, vertical stretch of 5. H value is -3, so remember opposite sign, and k value is -1. So we've got that translation 3 units left, down 1. We've got a vertical stretch of 5, and then the reflection over the x-axis. All right, so you take a shot at it, identify the transformations on the 2 given functions, pause the video, come back when you're ready to see the answers. Okay, so in this one, you're given the parent function f of x, log base 3 of x, and then you're given the transformed function for log base 3, x minus 1. So the base stayed the same, so we can compare these two as a transformation. If the base value changes, you cannot compare them using just straightforward transformations. So a value of 4, which means we have a vertical stretch by a factor of 4, and then we have x minus h, which means that h is equal to 1, so we have a translation right 1 unit. For the second one, it's log of x, remember that's a base 10, log base 10 of x, and we've got log base 10 of x minus 4 over 2 plus 7. That over 2, another way you can think about that is g of x is equal to a half log x minus 4 plus 7. This kind of lets you see that a value a little bit clearer. So that means we've got a vertical compression of a half. We have x minus h, so h is 4, k is 7, so we got a translation right 4 and up 7. All right, so some of the other characteristics that we're going to talk about are domain range, average rate of change, and then maybe writing the equation from a graph. So I'm not going to go through that skill today, but you guys know that from past. What you would do, you would just write out that g of x equals a log x minus h plus k, sub in your h and k values, sub in an x and a y value as well. So the k value is, remember, you have to be able to tell that from the first reference point. So that's the only way we're going to be able to pull out that k value. So there's no like horizontal asymptote to look for. You can find the h value from the vertical asymptote. K value is going to come from that first reference point. All right, so find the rate of change of the function and then identify domain and range. 3 questions, pause the video, take a shot at them, come back when you're ready to see the answer. Okay, so first one, we've got 4 log base 3, x plus 4 plus 2, and we've got from x equals 1 to x equals 5. So that is our domain interval. So we're going to need to know f of 1, and we're going to need to know f of 5. So what are the y values that go with that? So f of 1, we've got 4 times log base 3 of x plus 4, so that'll be 1 plus 4, which is 5, and plus 2. So for log base 3 of 5 plus 2, you're going to just have to evaluate that in a calculator to see what you get for that. As a reminder, for those of you using older calculators, you may have to change the base. So this could end up looking like 4 times log of 5 over log of 3, and then adding 2 to your answer. And that is 7.85989. So I'm going to round my final answer to hundredths, but until then, I'm going to keep my answer as accurate as possible. So 7.85989 is that first coordinate for me. And then for f of 5, we got 4 log base 3 of 5 plus 4, which would be 9, plus 2. So log base 3 of 9, I'm going to come over here. So log base 3 of 9. So one way we can think about that is 3 to the power of what is 9, or we can rewrite 9. So we could say this is log base 3 of 3 squared. Remember, if you have the same base value of a given value, it cancels out to be 1, and that exponent comes out here to the front, so this would be 2. So this one actually simplifies down to be 2. So we have 4 times 2 plus 2. 4 times 2 is 8, plus 2 is 10. So this one actually is a whole number coordinate. So we get 5, 10. And then we're doing our slope formula. So we'll have 10 minus 7.85989 over, we've got 5 minus 1. And that just goes straight into the calculator. So 10 minus, I'm actually going to even bring my answer in from that last time. So it actually keeps my overall answer even more accurate. So that's 2.140 divided by 4. So final answer is 0.5350, which would be 0.54. Average rate of change question again. G of x is a half ln x minus 2 plus 3 over the interval 4, 10, and rounds to the nearest hundredth. So we've got 2 to find again. So g of 4, half ln 4 minus 2 is 2, and then plus 3. So that's just going to go straight in our calculator. So we got a half ln of 2, so that's a natural log of 2, and then plus 3. Now, if you want to keep your answer 100% accurate, like you don't want to lose anything, what you would do is actually just put this in parentheses and say, okay, there's my y coordinate, so it's 4 comma this, and try and do your slope formula using all of that. You don't have to do that though. I'm okay if you put like a bunch of decimal places in just to keep a little bit of accuracy in there. So 3, 4, 6, 5, 7. So if I'm going to round to hundredths, I like to go a couple decimal places over that. And then g of 10. So we got a half ln of 10 minus 2 is 8 plus 3. So again, this could be my other coordinate, but I'm just going to evaluate it. So we got 0.5 times ln of 8 plus 3. That's 4.0397. 2. So I've got my slope formula now. 4.03972 minus 3.3657 all over 10 minus 4. 0.4657 divided by 6. So I get an average rate of change of 0.115525, which is approximately equal to 0.16 or 0.116. Identify domain and range of the function. So domain, this is one that's a little different from exponentials. Exponentials, it was unlimited, so it was negative infinity to positive infinity for the domain. It's kind of the opposite here. That's going to be the new range. So we've got an asymptote, vertical asymptote at h is 1, so at x equals 1. We have, it's going downwards, not that that matters, but it's still going to go to the right from there. So we haven't reflected it over the vertical axis. We've only reflected it horizontally, so that does not change the domain value at all. So the asymptote is at 1, which means that's not included. So domain is going to be 1 to positive infinity, and then our range, negative infinity to positive infinity. So it's, even though it's slowing down that rate of change as it gets further and further down x, it still keeps growing. So it's going to keep approaching positive infinity, just at a very slow rate. End behavior we don't typically see. You could say, like, as x approaches 1 from the positive side, the value approaches positive infinity or negative infinity, but it's complicated. We're not going to see end behavior on these. Okay, so that brings us to the end of today. Key points of a logarithmic function. You've got the vertical asymptote, the 2 reference points. Those are key. X-intercepts, y-intercepts, those are important too. So making sure you can figure those out algebraically and from looking at the graph. Transformations, you have an a, you have a h, and you have a k value. Make sure you can pick those out. Finding the key parts, such as the intercepts and average rate of change, make sure you can do that. So the given domain, whether it's 2 x values given to you or as an interval, make sure you can find both of those. All right, so at the end of today, you should be able to complete the questions in your Schoology folder. Talk to you soon.